The next two examples in the lesson deal with repeated zeros and what your graph looks like and how you can predict what your graph is going to look like when you have repeated zeros in your factorization. So it's along the same theme. We got to find the number of possible real zeros, the turning points, and all the real zeros by factoring. It's just that these are going to have some repeated zeros. And that may not mean a whole lot to you right now, but it will hopefully by the time we get done. What I want to illustrate to you is what happens once we get it in factored form and we have repeated zeros. So the first one I want to show you is this expression right here that's highlighted in blue. It's x times x minus 1 cubed times x plus 4. Now that's already in factored form, and what we're saying is that some of these factors are repeated. This x minus 1 factor is repeated 3 times. The x plus 4 is repeated twice. But our first factor here only has a multiplicity of 1. And when I say the word multiplicity, it just says how many times that factor is going to show up in your factorization. So this has a multiplicity of 1. The x minus 1 has a multiplicity of 3, and the x plus 4 has a multiplicity of 2. And just by knowing the multiplicity, you can make general assumptions and predictions of what your graph is going to look like. And we're going to try to piece this together. So I'm going to show you the graph, and I'm going to talk through how you know what the graph is going to look like. So here's a part of that graph. It gets quite large, so if I zoom out and show you the whole thing, just zooming out with the y's, you can see the entire graph. It's a polynomial function. It's smooth. It's continuous. If I go back to the equation, I wanted to show you that this is a x to the first. This will end up being an x to the third by the time we end up multiplying all those together. This will be x squared by the time you multiply all those together. So you're going to have an x times an x to the third times an x to the second. And that'll give us an x to the sixth. This is going to end up being a 6-degree polynomial if we were to multiply those all together by distributing. So the only reason I bring that up is you can clearly see that that's the nature of this graph as I make the y's bigger and bigger. Look at the end behavior. It's a 6-degree polynomial, therefore the end behavior has to be the same. They're both going to positive infinity. Now let's focus on the issue at hand, and that is, what about these multiplicities? So if you look at this, at the -4, what we call this is a line that's coming down, your curve's coming down, and is tangent to the x-axis. Anytime that is tangent to the x-axis, you have to have had a multiplicity that is even. Another way of saying it, that must have been an x plus 4 squared or higher in an even power. Okay, because it's tangent. Now I want to show you the other ones over here. This one here is coming right down through, and it crosses through the x-axis. If it crosses the x-axis, anytime it crosses, here's what you know. You know you have an odd multiplicity. Okay, abbreviate that. If it crosses, it's an odd multiplicity. If it strictly just crosses without flattening, it'll have a multiplicity of 1. So this one, because it's crossing but doesn't flatten, I'm thinking has a multiplicity of 1, so it better be x to the first power. Since it's crossing here at 0, I could think of it as x minus 0, or x plus 0 for that matter, to the first power. Now what's different about this next one, it's still crossing, so because the graph comes through and crosses the x-axis, I know it has to be an odd multiplicity. But the difference between this one and this one is how this graph flattens. So I'm going to erase some of this so that you can see it better, but you can clearly see that this one has a different aspect to the graph than this one does. When they cross, think of degree 1. It's a multiplicity of 1. If it flattens and cross, we're probably thinking a multiplicity of 3. Now it's hard to tell if it's 3 or 5, so we'll probably keep things fairly simple here, and we'll talk about multiplicities of 3, 2, or 1. But because it's crossing here at a positive 1, that means our factor had to be x minus 1. We're thinking it has a multiplicity of 3 because it flattens and crosses. So what I want to illustrate here is if it's tangent to the axis, the x-axis, you've got to be thinking even multiplicity. That means the power on that factor has to be even. If it crosses but doesn't flatten, we're going to think it's a power of 1. If it crosses but does flatten, we're thinking it's a higher odd power. Typically, it's going to be 3. I'm not going to say absolute. For sure it's 3. We can have higher powers if we like, but it's very hard to distinguish between them. So that's one of the graphs I wanted you to look at. So now if we look at this one, I highlight this rule, we should be able to predict the nature of the graph because both of these factors have a multiplicity of 2. Because 2 is even, that means that these locations where x is equal to 0, or the zeros are a function, well, if x plus 1 is a factor, that means x is a negative 1, has to be our 0, because x minus 3 is a factor, x equals 3 has to be a 0. So at a negative 1 and a positive 3, we should be seeing this tangent behavior in the graph. And I'll blow that graph up, which I have down below there. Here is our graph. And at the exact locations that we were talking about, we see the graphs are tangent. Okay? Even powers are going to be tangent to. Odd powers will be crossing, and sometimes they flatten. One thing I didn't get in here to illustrate, I do want to show you the difference between a second degree and a fourth degree multiplicity. So I'll type that in quickly. We'll go y equals, and we'll go x minus 1 raised to the second. We got to take that times maybe an x plus 3 raised to the fourth. And now these numbers get quite large very quickly. So I want to graph this on this coordinate plane. Get rid of that one. Okay, so it's hard to see all that graph in there, so I'm going to zoom out. And there's your graph. If you want to see what the entire graph looks like, there it is, at least most of the graph. Going back to our equation, this is, and again, just trying to piece together some more pieces of the puzzle. This is a second degree, that's a fourth degree. So by the time we get done doing our distributing, this will give us an x squared. This will give us an x to the fourth. We'd have to take an x to the fourth times x squared. It'll be a x to the sixth. And all x to the sixth graphs are a U-shaped graph, and that's what you're seeing here. So just quickly going back to this graph, the point I wanted to make a point of emphasis on is that we had x equals a negative 3 as one of our zeros, but this had a factor of x plus 3 to the fourth power. This one has x-intercept at x equals 1, which means the factor had to be x minus 1, and this one was raised to the second power. So here's the thread. Even powers are always going to be tangent to the curve. They'll come down here and they'll get close to, and they'll touch it in one place. And this graph's going to touch it at a negative 3. But when it was a second degree power, you see the difference is that it's not as flat. So the higher the power is, the flatter it will be, but it will still be tangent to. And that's a theme that's going to be a similar theme even with odds. The bigger the power, the flatter it is by that point of intersection with the x-axis. So show you another example here. This one is x minus 2 cubed times x plus 4 cubed. 2 cubics are going to make a 6th degree polynomial, so you're going to see a W shape or a U shape again, opening upward. What we should be able to determine is at x equals 2, since it's minus 2, at x equals 2 is a 0. At x plus 4, that means at x equals a negative 4, we should see something happening around these multiple or repeated zeros. Because these are both odd powers, what we're going to see in our graph is that they are going to cross but flatten. And here is that graph shown. At a negative 4, our graph is coming downhill, it's going to cross, and it's flattening. It's a dead giveaway that it's a multiplicity or a power that is odd on your curve. So that's a repeated zero, both at negative 4 and positive 2. So with that said, what I want to do is go back into our examples and finish this off. So state the number of possible zeros. Okay, nothing different here. It's a third degree polynomial, and because it's a third degree polynomial, the number of zeros is the maximum. Is 3, it can go down to 1. Anywhere from 3 to 1 zeros. Turning points, okay, because it's an odd and it's a third degree, odds always have an even number of turning points. It's either 2 or 0. The next thing, and this is the area of focus on these problems, and that is find the real zeros by factoring. So we're going to put 0 equals negative 2x cubed minus 4x squared plus 16x. This time we have a monomial factor that we can pull out, and I'm going to factor out in this case as well. I don't like leading coefficients that are negative, and I also have 2's that are available in all these. So I'm going to pull out a negative 2 x. That is the greatest common factor of those three terms. Factoring that out. You factor out a negative, it changes all of the signs, so this will become a positive, so it's going to be a positive x squared. I take a negative 4 divided by negative 2, that is a positive, it'll change its sign, and I'll be left with 2x, and then I'm going to take a negative out of a positive, which will be negative, and 16 divided by negative 2 is a negative 8, and x divided by x is 1. So there's my factorization. I'm not completely finished with this factorization because this will factor again as well. So equals a negative 2 times x, and then what are the factors of 8 that give you a 2? So we've got x and x plus and minus, factors of 8 that are 2 apart, 4 and 2. There's no multiplicity whatsoever in this problem. So what they did is they gave us another example where we can just find the number of zeros. One of the zeros is when x equals 0, when x is a negative 4, and when x is a positive 2. So no real changes here. Now let's take a look at 5b. In 5b, fifth degree polynomial, so we have a total number of zeros. The maximum it can have is 5. Since it's odd, the fewest it can have is 1. Number of turning points, the maximum it can have is 1 less than the power, so 4, and every even number below that, so 2 and 0. Solving by factoring, we're going to put in a 0, and then we're going to take 3x to the 5th minus 18x to the 4th plus 27x cubed, and we're going to do our best to factor this. So, what can factor out of all three of these terms? Well, all these numbers are divisible by 3, and the greatest number of x's that we can factor out is x cubed. So I'm going to take out a 3x cubed in my first monomial factorization. If I take out a 3x cubed, we're left with an x squared minus 6x plus, and a 27x cubed divided by 3x cubed gives us a 9. So, finish our factorization. X squared minus 6x plus 9. X squared is x times x. Signs have to be the same. Minus and minus because of our negative 6. 3 and 3. Here's the example that they were talking about. We've got a couple of multiplicities or repeated zeros here. It's 3 times x to the 3rd. There's a repeated 0. Then we got x minus 3 squared. That factor is repeated, so that's a repeated 0. So what we're looking at then is a repeated 0 at x equals 0. Because it's a power of 3, we know when it crosses 0, it's going to flatten and cross at 0. And then at a negative 3, or when x is equal to a positive 3, we have another 0. So once we get out here to a positive 3, 1, 2, 3, we should have this graph coming down in tangent to. So it's going to be coming down here, touching and going back up. So I'm going to put all this information together and try to sketch a graph with this. They don't ask us to, but we're going to anyway. So because this was a fifth degree polynomial and the leading coefficient was positive, I know I've got a graph that's coming from low and finishing high. The other things that I know is that it crosses the x-axis at 0 and at 3, and we have multiplicities. I know it's crossing at 0 because it has a odd multiplicity. It's going to come up through 0 and it's going to flatten, but it's got to cross. So there's at 0. Then when we get to 3, 3 had a multiplicity of 2. So I come out here to 1, 2, 3. Here's where 3 is. Our graph has to come up. It's going to come back down and touch and just kiss that graph once and come all the way back up. Because it's an odd degree polynomial, I've got everything in line. It starts from low, it finishes high, it crosses through 0, it's a power or a multiplicity of 3, repeated 3, so it flattens and crosses. At a positive 3, it was a multiplicity of 2, or it had a power of 2 for repeated zeros. Anytime it's even, it comes down, touches, and is tangent to, and comes back up and finishes with the opposite end behavior. So being able to manage and figure out the multiplicity of zeros helps you know how to sketch the graph and know what to expect when you graph it on your calculator.